Good morning, everyone. Myself Muskan, BSc Chemistry Honors first year. Today, I will discuss the chapter structure and bonding. Let's start the chapter. Although most abundant element in the earth crust are oxygen, silicon, aluminium, and other lighter atoms, yet strangely enough, almost 98% of the living tissue are made up of carbon, hydrogen, oxygen, and nitrogen. The carbon be the central atom around which the chemistry of life is process and revolve. The key role in the origin and evolution of life is of carbon due to its distinct property of combining or sharing electron with other carbon atoms to form a wide variety of linear branched and cyclic chain having carbon to carbon covalent bond. This self linkage property of a carbon atom is called catenation. The force of attraction which binds the atom together in a molecule is called chemical bond. The property of a compound depend upon the linkage present in it. The chemical bond may be covalent, coordinate, ionic, van der Waal, and hydrogen bonding. Nature of bonding in organic compound. The bonding in the organic compound depend upon first is configuration of the central atom. The electric configuration of the central atom is, that is, the carbon can form a maximum of four bonds, but the type of bond formed depend upon the hybridization of carbon. Second one is hybridization of carbon. The hybridization of carbon atom affect the several physical and chemical properties like bond length, bond energy, acidity of organic molecule. Now we will discuss hybridization, the process of intermixing of atomic orbital of the same atom having nearly the same energy such a way that they redistribute their energy and give the same number of new orbital called hybrid orbital of same shape and energy is called hybridization. The property of hybridization orbital are entirely different from those of atomic orbital from which these have been obtained by hybridization. Hybridization does not take place in isolated atoms, and the hybrid orbital are formed only at the time of bond formation. Since hybrid orbital are stronger pi bond, therefore carbon and other atom undergo hybridization prior to bond formation. Now we will discuss characteristic of hybridization. The characteristics of hybridization include condition for hybridization and properties of hybridization hybrid orbital. Conditions for hybridization. The hybridization take place only during the bond formation, that is, hybridization never occur in separate atom. The hybridization take place using valence orbital, that is spdf subshell of the same atom. The hybridization take place only among the orbital having small energy difference. Half filled, completely filled, and vacant filled of the atom can take part in hybridization. The excitation of electron from lower shell to higher subshell is not necessary during hybridization. Properties of hybrid orbital. The number of hybrid orbital formed is equal to the number of atomic orbital taking part in the hybridization. The orbital hybrid orbital formed have identical shape and energy. The hybrid orbital has two lobes, one lobe larger lobe and the other smaller lobe. The larger lobe has more electron density than the smaller lobe. Thus, the larger lobe is used during overlapping of orbital. The hybrid orbital from stronger sigma bond than the atomic orbital taking part in hybridization because the hybrid orbital can overlap to a greater extent. Each hybrid orbital cannot have more than two electron with opposite spin. The hybrid orbital orient themselves in the space at maximum distance apart to acquire minimum interelectronic repulsion and maximum stability. Hence, the type of hybridization tells about the shape geometry of the molecule. Now we will discuss type of hybridization. The hybridization can be of different type, but the carbon atom can show the following three type of hybridization. First one is diagonal or sp hybridization. The hybridization in which one s and one p intermix to give two sp orbital which has same energy and identical shape is called sp hybridization. The two hybridization orbital orient themselves in space at an angle of 180 to give their shape by acquiring minimum electronic repulsion, minimum energy, maximum stability. Hence the hybridization is called diagonal hybridization or linear hybridization. Each hybrid orbital contain one electron and has 50% s character and 50% p character. In the formation of acetylene molecule, each of the two carbon atom undergo sp hybridization to form two sp hybrid orbital which are collinear. In addition, each carbon atom has two unhybridized p orbital, 2ps and 2py, 2py and 2px, which are at right angle to each other, and also the two sp hybrid orbital. The promotion of electron followed by hybridization process is shown in that figure. One sp orbital of one carbon atom overlap with one sp hybrid orbital of the other carbon along their internuclear axis to the sigma bond between them. The other sp orbital of each carbon atom overlap with one s orbital of hydrogen atom along their internuclear axis to form ch bond. Since all the four atoms lie in a straight line, acetylene is a linear molecule. The 2px orbital undergoes sideways overlapping to form pi bond between the two carbon atom. Similarly, 2py orbital of both carbon also overlap sidewise to form pi bond. Thus, the two bond of are at right angle to each other. If the electron cloud of one pi bond is considered to be above and below the line joining the two carbon atom, then the word lie in front of and behind this line. In actual practice, however, this merge with the internuclear axis, due to which the electron density cloud appears cylindrical and its cylindric is it is symmetrical, also shown in that figure. Various parameters of acetylene molecule are bond angle, that is HCC is 180 degree Celsius degree. C triple bond C bond length is 1.20 Armstrong or 120 picometer. CH bond length is 1.06 Armstrong or 106 picometer. C triple bond C bond strength is 200 kilocalorie mole inverse or 836.6 kilojoule per mole. These parameters for acetylene molecule can be depicted. The Lewis structure of acetylene is this. Second, we will discuss trigonal or sp2 hybridization. The hybridization in which one s or two p orbital intermix to give three sp2 hybridization orbital which have same energy and identical shape is called sp2 hybridization. The three sp2 hybridization are oriented in space at an angle of 120 degree to acquire trigonal planar shape by acquiring minimum inter-electronic repulsion, maximum stability, and minimum energy. Hence, the sp2 hybridization is called triangular hybridization. Each of the sp2 hybridization has 33% of S character and 66.67% of P character. This type of hybridization explains the structure of all compound of porot such as BF2, BCl3, BH3, etc. All compound of carbon having a double bond between carbon atom, ethylene, and third one is in conjugated denies or polyenes. Example 1 3 butadiene. Shape of ethylene, that is C2H4. The electronic configuration of carbon is in the excited state is 1s2, 2s1, 2p1x, 2py1, 2pz1. In the formation of ethylene molecule, each of the two carbon atom undergo sp2 hybridization to form three sp2 hybrid orbital. Beside these three sp2 hybridized orbital, each carbon atom has one unhybridized 2p orbital, which is oriented at a right angle to the plane of the 3sp2 hybridized orbital. The process of electron promotion and hybridization is shown in the figure. One of the sp2 hybrid orbital of the carbon atom overlap coaxially with one sp2 orbital of the other carbon atom along their internuclear axis to form a C sigma bond between them. The remaining two sp2 hybrid orbital of each carbon atom overlap with one s orbital of two hydrogen atom along their respective internuclear axes to form CH sigma bond. The unhybridized 2p orbital of the both carbon atom overlap sidewise to small extent to form a weak pi bond as shown in figure. Thus, ethylene is a planar molecule. Various parameters of ethylene molecule are C double bond C bond length is 1.34 Armstrong. C H bone length is 1.09 Armstrong. HCH bone angle is 117.5 degree. CCH bone angle is 121 degree. The Lewis dot structure of the ethylene is given. Now we will discuss tetrahedral or sp3 hybridization. The hybridization in which one s orbital and 3p orbital intermixed to give 4 sp3 hybrid orbital which have same energy and identical shape is called sp3 hybridization. The 4 sp3 hybrid are oriented in space at an angle of 109 degree 28 minute to acquire tetrahedral shape by acquiring minimum interelectronic repulsion, minimum energy, and maximum stability. Hence, the sp3 hybridization is also called tetrahedral hybridization. Each sp3 orbital has 25% S character and 75% P character. This type of hybridization occur in all compound of carbon which contain carbon carbon single bond, that is methane, ethane, etc. The shape of methane. Atomic number of carbon is 6. So its electronic configuration in the ground state is 1s2, 2s2, 2p(x1), 2py1, 2pz0. Due to unpaired electron in the ground state of carbon should show a valency of 2. However, the carbon exhibits a valency of a 4. It therefore must have 4 unpaired electron. This is possible only when one electron from 2s orbital is excited to the empty 2pz orbital. To give excited state, the electronic configuration become 1s2, 2s2, 2px1, 2py1, 2pz1. The process of electron permutation and hybridization is shown as below. And 1 2s orbital and 3 2p orbital of the carbon atom hybridized to form 4 sp3 hybrid orbital. These hybrid orbital of the carbon atom are directed towards the four corner of regular tetrahedron and are arranged at an angle of 109 degree 28 minutes to each other. Each of the four sp3 hybrid orbital overlap coaxially with one s of a hydrogen atom. Atomic number is of H is 1 and its electronic configuration is 1s1 to form methane molecule, which has a symmetrical tetrahedral structure as shown in the figure. Various parameters of the methane molecule are bond length. Bond length of CH is 1.10 Armstrong. Bond angle of CHCH is 109 degree 28 minute, and the Lewis dot structure is given in the figure. Now we will discuss the shape of ethane. In the formation of this molecule, one of the sp3 orbital of one carbon overlap on one of the sp3 orbital of the carbon atom to form a C sigma bond. The other three sp3 orbital of each carbon overlap coaxially with the 1s orbital of hydrogen to form CH sigma bond. Various parameter of ethane is like methane, the CCH or HCH bond angle is 109 degree 28 minute, and the CH bond length is 110 picometer. CC bond length is 154 picometer. CC bond dissociation energy is 348 kilojoule per mole. The structure of CH3F, CH2, Cl2, C2H5Cl are derived in a similar manner. Note, there are some molecules which have sp3 hybridization, but the bond angle is of 109 degree 28 minute and the shape is not tetrahedral. Example H2O and H3, which have bond angle of 104.5 degree and 107 respectively, have bent shape and pyramidal shape respectively. The most stable angle is tetrahedral angle, that is 109 degree 28 minute. Determination of hybridization of central atom. The hybridization of central atom can be defined as in different ways. First one is the hybridization of central atom can be determined by calculating the hybrid state number of the central atom. Hc is equal to 1 by 2 Vc plus Mc minus C plus A, where Hc is the hybrid state of central atom, Vc is the number of valence shell electron in central atom, C is charge on positive charged species, and A is charge on negative charged species. Second one is the hybridization of central atom can be determined by calculating the hybrid state number of the central atom by counting the number of sigma bond and lone pair electron in the given shape. Hc is equal to sigma bond plus lone pair. Bond length. The average distance in between the center of two atomic nuclei in the covalent molecule is called bond distance or bond length. The bond length has characteristic property of a molecule and give information about its structure properties, etc. Bond length can be determined by X-ray diffraction, electron diffraction, or other spectroscopic studies. Unit of bond length is Armstrong or picometer. Bond length of some common covalent compound is given. That is CC single bond length is 1.54 Armstrong. C double bond C bond length is 1.34 Armstrong. C triple bond C bond length is 1.20 Armstrong. Factor affecting the bond length. First one is the size of atom. The bond length is directly proportional to the size of atom, that is bond length alpha size of atom. So we can say the larger the size of atom, longer will be the bond length. Example, the bond length order among the hydrogen halide is as the most bond length is in Hi, then HBr, then HCl, and smallest one is in HF. On moving down, the group 17 hydride, the size of X atom increase, thus the internuclear distance between H and X atom increase. So the HX bond length is also increase. Second one is the multiplicity of the bond. The bond multiplicity is defined as the number of bonds present in two covalently bonded atoms. The bond length is inversely proportional to the multiplicity of the bond. Bond length directly proportional to the 1 by multiplicity of the bond. So we can say that the more number of bond, smaller will be the bond length, because with the increase of the number of bond, the force of attraction between the two atoms increases, and thus the two atoms come closer to each other, so the bond length decreases. The bond length of the order among the C single bond C, C double bond C, and C triple bond C. The maximum bond length in C single bond C, then C double bond C, and minimum in C triple bond C. C single bond C is 1.54 Armstrong, while C triple bond C is 1.20 Armstrong. The third reason is the type of hybridization, that is percentage of S character. The bond length is inversely proportional to the percentage of S character, that is bond length inversely proportional to the percentage of S character. So we can say that more the percentage S character will more be the electronegativity, and thus more be their attraction with the neighboring atom. So small will be the bond length. Example, CH bond length among the CH double bond CH and triple bond CH bond, because in single bond CH, double bond CH, triple bond CH, the hybridization of carbon atom is different. Thus, 3 occur more attraction in between CH in triple bond CH bond than in double bond CH, and then in single bond CH. Now fourth one is delocalization of electron. With the delocalization of pi electron over conjugated system, bond length de- decrease from single bond and increased for double bond. For example, in benzene there are three carbon single bond carbon and three carbon double bond carbon. The expected value of the bond length is 1.54 Armstrong and 1.34 Armstrong respectively. Actually, in benzene, the delocalization of electron cloud take place and all bond length become equal, that is 1.397 Armstrong. Bond energy, the average amount of energy released when one mole of bond are formed from isolated gaseous atom is called bond energy. We always take the average value of bond energy because the bond energy of a particular atom is not same in different type of compound and even not same in the same compound. Bond strength are usually calculated from the value of a heat of formation or heat of combustion using hash law of constant heat summation. Some of the important bond energy are given in table. Factor affecting bond energy. Size of atom. The bond energy is inversely proportional to the size of the atom. So we can say that larger the size of the atom, longer will be the bond length, thus less energy will be required to break the bond, that is lesser will be the bond energy. Second one is multiplicity of the bond. The bond energy is directly proportional to the multiplicity of the bond. The bond energy the bond energy changes, that is, we can say that more the number of the bond in between the two atom, smaller will be the bond length, thus more will be the energy is required to break the bond, that is more will be the bond energy. Third one is the number of lone pair electrons. The bond energy is inversely proportional to the lone pair present in the bond atom. So we can say the presence of lone pair on the bond atom cause repulsion between the atom and less amount of energy is required to separate the bonded atom, less will be the bond energy. Now we will discuss bond length. The angle between any two adjacent bond emerged from the same central atom in the molecule is called bond length. The bond length is expressed in degrees, minutes, and seconds. The bond length is determined by X-ray diffraction experiment and electron diffraction method. Factor affecting bond length. Hybridization. For molecule having sp3 hybridization, the bond angle is 109.5 degree, whereas the bond angle for sp2 and sp molecules are 120 and 180 respectively. Nature of the atom attached. For same hybridization, sometimes bond angle deviate due to the presence of atom having different electronegativity. HCS angle in N propane is 109 degree, while in BRCC angle in 1 bromopropane is 114.2 degree. The comparison of bond length in between the compound when central atom is here but neighboring attached atom is different. The bond angle in ammonia is 107 degree Celsius degree. Let's say, but the bond angle in NF3 is 102.4 degree. Reason: due to the high electronegativity of F atom in NF3 than H atom in NH3, the bond pair electron in NF3 are far away from the central atom, that is N in NH3. So there occur more bond pair repulsion in NH3 and than in NF3. Hence the bond length of NH3 is higher than the NF3. Size of the atom: bond angle changes with the increase in the size of central atom. For example, H2O. H angle is 104.5 degree, while in H2S, HSH angle is 92.1 degree. Comparison in bond angles in between the compound with central atom is different. Lone pair electrons are same, but neighboring are different. The bond angle in water is 104.5 degree, but the bond angle in H2S is 90 degree. Reason is due to high electronegativity of O atom and then S atom, the bond pair electron of OH bond are more closer to the central atom O in water than the bond pair of electron of SH bond towards the S atom in H2S. So there occur bond pair repulsion in the H2O and then in H2S. Hence the bond angle of H2O is higher than in H2S. The bond angle of ammonia is higher than phosphine. The reason is due to high electronegativity of N atom in NH3 than P atom of PH3, the bond pair electrons of NH are more closer to the central N atom in ammonia than the bond pair of bond pair electron of pH bond towards the central atom P in pH3. So there occur more bond pair repulsion in NH3 than in pH3. Hence the bond angle of ammonia, that is NH3, is higher than phosphine, that is pH3. Presence of lone pair: in molecule having regular geometries, the bond angles are dependent upon hybridization of central atom. The molecules having lone pair of electrons on the central atom, the unequal repulsion between bond pair and lone pair is distorted geometry with changed bond length. For example, NH3 is 107 degree rather than the normal bond angle of 109 degree 28 minute. In water, it is 104.5 degree because of the lone pair bond pair repulsion. Comparison: the bond angles in between the compound when central atom is different along with different number of lone pair, but neighbor atoms are same. Bond angle among CH3 NH3 H2O is more maximum bond angle in CH3 than NH3 and minimum in H2O. The reason is order of repulsion in between the different type of electron is maximum in lone pair repulsion, then lone pair bond pair, and the minimum repulsion take place in bond pair, as there occur lone pair repulsion in H2O, while lone pair bond pair repulsion in NH3 and bond pair repulsion in CH4. The bond angle decrease to a large extent of water than in ammonia form from a tetrahedral angle in methane. Thus, the trend of both bond angle along CH3, NH3, and H2O is maximum in CH3 and minimamine H2. Now we will discuss covalent bond. The bond which is formed by mutual sharing of electrons in between the same or different atom of atom is called covalent bond. Classification of covalent bond on the basis of bond order. First one is single bond. The bond which is formed by sharing of only one electron in between atoms is called single bond. These atom is formed by axial overlapping in between the two orbitals. The bond is always a sigma bond, can never be a pi bond, because the atom forming single bond prefer to form a strong sigma bond rather than a weak pi bond. Multiple bond, the bond which is formed by sharing of two or more electron pair in between two atoms is called multiple bond. It may be double or triple. Double bond, the bond in which formed by sharing of two electron pair in between two atom is called double bond. One, it contain one sigma bond and one pi bond. Triple bond, the bond in which bond is formed by sharing of three electron pair between the two atom called triple bond. It contain one sigma and two pi bond. Localized and delocalized covalent bond. Localized covalent bond are those bonds in which the electron pair do not move from their position. The sigma bond will be localized if it is not involved in hyperconjugation. Similarly, and pi bond will be localized if it is not in conjugation with other molecule, with other multiple bonded with heteronuclear atom having positive charge, negative charge, odd electron and non-bond electron. Delocalized covalent bond, the ability of pi electron to participate in more than one bond formation is called delocalization of electron. Such a bond formed may change their position with one another. Such bonds are called delocalized bond. The delocalization of electron always result in a strongly bonded stable molecule. Following type of molecule may have delocalized bond. Molecules having double and triple bond in conjugation. Second, the molecule having double and triple bond in conjugation with the p orbital of an adjacent atom. Third one is hyperconjugation. Now we will discuss conjugation. The presence of lone pair, positive or negative charge, multiple bond at alternate position with respect to a double bond in a cyclic or acyclic system is called conjugation. Now we will discuss alternate and non-alternate hydrocarbons. Alternate hydrocarbons, the conjugated hydrocarbons in which the stars are placed on alternate conjugation carbon atom. That is, no two star are present in adjacent carbon atom is called alternate hydrocarbons. Non-alternate hydrocarbons, the conjugated hydrocarbons in which two star is present on two or more adjacent conjugated carbon atom are called non-alternate hydrocarbons. Alternate system can be further subdivided. The system is even alternate if equal number of starred and unstarred carbon occur. It is odd alternate if the number of two sets are not equal. Since we always maximize the number of star, this means that the old alternate system will have more starred than unstarred atom. Now we will discuss intermolecular forces. The forces that is attractive or repulsive in between the atom or molecule are called intermolecular forces. The term does not include the electrostatic that exist in between the two oppositely charged ionic or metallic. This term also does not include the force which hold the atom in the of the molecule together, covalent bond and coordinate bond, and the ionic ion dipole attraction. The interactive molecular forces are van der Waals forces. Type of van der Waals forces. The van der Waals forces are of the following types. First one is dispersion forces. The weak induced dipole traction in between the isolated atom is called dispersion forces. The force of attraction was first proposed by German physicist Fritz London. So it is also called London forces. These attractive forces are inversely proportional to the sixth power of the distance in between the two interacting particle. They act only at a short distance. It is very weak bond, and it can be exist in between every molecule. The van der Waals attraction depend upon the size of atom. More is the surface, more will be the magnitude of the van der Waals forces, and vice versa. Factor affecting the van der Waals interaction. First one is size and shape of the molecule. The van der Waals forces are short range attractive forces operating in non-polar molecule. These forces depend upon the surface area of the molecule. With the increase of surface area or molecular mass, the magnitude of attractive forces increase. The effect of size can be seen in the boiling point of a few alkanes that are given below. The boiling point increase with increase in molecular mass of the alkene. It also increases with the increase of surface area of the molecule. For example, the boiling point of n-butane is higher than isobutane due to its greater surface area. Second one is temperature and pressure condition. The magnitude of van der Waals interaction at low temperature and high pressure. With the decrease in temperature, the entropy of molecule decrease. They become more ordered and suitable in induced dipole. With the increase of pressure, the volume decrease. The number of molecule per unit volume increase. The magnitude of van der Waals forces increase. Third one is atomic number. Van der Waals interaction increase with the increase of atomic number of atom. This is due to the increase of size as well as number of electron in the atom. Second one is dipole induced dipole forces. The forces which which act in between the molecule having permanent dipole and the molecule having no dipole is called dipole induced dipole forces. The molecule having permanent dipole induce the dipole in the other molecule. This attraction is stronger than the London forces. The attractive forces is inversely proportional to the sixth power of the distance between the two interacting particles. Cause of solubility of noble gases in water. The H2O molecule causes the distortion of symmetrical valence electron cloud of the noble gas, and thus the water molecule induce the dipole to the noble gases. So dipole induced dipole interaction take place in between the noble gases and water molecule, which result in the solubility of noble gases in water. Now, third one, we will discuss dipole forces. The forces which are in between the molecule having permanent dipole are called dipole forces or Kisome forces. The attraction is stronger in London forces but weaker than ion attraction. Because the partial charges are involved, the attractive force is inversely proportional to the third power of the distance in between the interacting particle. Now we will discuss hydrogen bonding. The weak electrostatic force of the attraction in which the hydrogen atom and the electronegative element is called H hydrogen bond. The hydrogen bond is represented by a dotted line. It is much less strength than the covalent bond and is essential the result of electrostatic interaction, delocalization effect, and dispersion effect. The hydrogen bond energy is in range of 3 to 10 kilo kilocalorie per mole as compared to the covalent bond. Condition for H hydrogen bond formation: the molecule must have H atom, and second one is the H atom must be attached to a more electronegative element, because more the electronegativity of the element, more will be the separation of charge in the atom between the H atom and the electronegative atom. Thus more will be the attraction in between the slight positive charge at atom and slight negative electronegative element, and strong will be the H bond. Type of hydrogen bonding: first one is intermolecular hydrogen bonding. Inter means in between. The hydrogen bonding in which formed in which between the same or different molecule is called intermolecular hydrogen bonding. Intramolecular hydrogen bonding. Means within. The hydrogen bond which is formed within the same molecule is called hydrogen bonding. Requirement for intramolecular hydrogen bonding: the two groups satisfying the condition for H hydrogen bond must be present in ortho to each other. The molecule must be planar. The hydrogen bonding should lead to the formation of six-membered ring structure having H atom. Effect of consequence of hydrogen bonding: the hydrogen bonding affect the different property, that is dissociation. In aqueous solution, HF dissociate to give HF negative, HF2 negative. We will discuss um, dissociation, and we are on the topic HF2 ion. Note in F negative ion to the hydrogen bonding in HF. This explain the existence of KHF2. Melting and boiling point: due to the formation of H bond in between the molecule, so extra heat is required to break this bond. So the melting point and boiling point will be the high. Example: boiling point of ethanol is higher than ether. The hydrogen bond is formed in between the ethanol molecule, not in the between the ether molecule. There can be only weak van der Waals forces in between the ether molecule. As more heat is required to break the hydrogen bonding than the van der Waals bonding, hence the boiling point of the ethanol is greater. Now our next topic is solubility. Due to the formation of hydrogen bonding in between the covalent molecule and water molecule, the covalent compound will be soluble in water. Now next is viscosity and surface tension. The compound which can formed H bonding in between the own molecule can exist as associated molecule, and thus their molecule cannot flow easily. So the compounds will have high viscosity and high surface tension. Due to the small Now one question is, H2 is liquid while H2S is gas. Due to the small size and high electronegative atom of O atom and S atom, the H bond is formed in between H2O molecule, not in H2S molecule. There will be only weak van der Waals force in between the H2S molecule. So H2O is liquid and H2S is gas. Now we will discuss the strength of the bonds. Ionic bonds have maximum strength, then covalent bond, then metallic bond, then hydrogen bond, then van der Waals bond, in which dipole dipole has maximum, then dipole induced dipole, and the induced dipole has minimum strength. मतलब means less energy is required to break the induced dipole bond. The attraction in between the following species: group 18 to group 18, induced dipole attraction is there. In O2 and O2, induced dipole is there. CO2 CO2, induced dipole and induced dipole attraction is there. Group 18 and H2O. As we know, H2O is a polar compound, and group 18 is no, non-dipole so induced dipole and dipole attraction is there. H2O is a polar compound, that is, it has dipole, so it contain dipole attraction or H bonding. NaCl and H2O, NaCl can be dissociated into ions, and H2O is a dipole or polar compound. So in between these, ion and dipole attraction is there. It's let's done our first part, and now we will discuss the other host ghost addition reaction in the other video. Till then, bye.